Okay. Hello, my name is Stian, and I'm the person that rewrote and ported OpenQB Player over to Linux and BSD. And then many probably has a question why. And to do that, I want to step back in time a bit to my childhood. So the very first computer me and my brother had was an old Apple IIe. And we received that with a couple of games and a basic tutorial. So that got me curious into software programming a bit. And of course, we also had an old game console that we could connect to our TV. But as we grew older, my big brother bought a computer. And this had the awesome specifications of a 33 megahertz CPU that we, of course, upgraded to 66 megahertz. It had a whopping 4 megabytes of memory that, of course, we could upgrade to 20, still not so much, and 200 megabytes of storage. And most of you can probably guess that if you have an MP3 collection of music, you cannot fit so much music on this computer, which means that back in the days, we had other means of music, which we back then called module files or Amiga modules. But this computer only had a PC speaker, or what's known as a beeper. And I will do a little quick demo about how music would sound on such a machine. So we had inertia player, which could actually output audio into the speaker. And the music quality would then come out of the speaker, so it would be even worse than this. But at least it was music. So yes, let's get that out of the way again. I need to get the mouse out. Okay. Easier. So yes. So my brother, he decided that we wanted to have some better audio quality. So he bought an audio card, which was a clone of an Samblaster card. And with that, we could suddenly have better music, and we could also have music in our games as well. And at this time, we also got access to QB Player, which I found to be an awesome software. So let me get DOSBox up and running again. 2 seconds. So you would be presented with a file browser similar to like this. And your music would be presented with nice colors. And the audio was much better as well. And for me, my entire childhood of music was in software like this. So yes, I really miss those days from my childhood. I have a nostalgia for it. So, for our computer, I started to learn programming with Turbo Pascal. And the available information for that was not that great. My local library had some few books of it. All the books seems to really go into learning to make like an inventory of your music collection. And that was kind of the level you would learn about when you read those books. So later in high school, I learned a new programming language, Delphi, which basically was Pascal wrapped into Windows instead. So I didn't quite get so much more use out of that. But some friends in the class above me introduced me to Linux. And he gave me a copy of a Linux distribution on CDs. And with those were also source of everything. And suddenly you could go into depth of every part of the machine. Anything you wondered how it worked, you could find the source code. If you wanted to make your own things, you could copy-paste from other things. So for me, open source was a real opener for learning how to program. But music back in 2000 on Linux was not that much fun, though. We had a mic mod to play modules. Back then it didn't have colors yet, but I didn't manage to find screenshots on Google. That was that old actually. And if you run a graphical environment, you could have XMS and similar players, but it didn't give me quite the feeling if you want to play old Amiga files. It didn't show you anything about how it actually worked. And I really missed it. It had that old nostalgic feeling that could never really be solved. So I kept on watching on QCubic Player, and one day they had renamed it to OpenCubic Player and released the source. Yes! And if anything is open source, that means that everybody can use it straight off. Like, that's how it works, right? No, it just means that you could compile it on DOS. Didn't really help that much on Linux, so I felt a bit disappointed as well. But hey, what can you do when you are young? You download it and you take a look inside. And for me, what I did is that I started just with a blank project. And I started first to copy over the main function. But let's first take a little look of DOS. DOS is what many of you have never used. It's a disk operating system. And as the name implies, it has a file system API. So yes, but if you had graphics, that means that your software would talk directly to the graphic card. So that doesn't port well into Linux. Memory management, well, you had a 1 megabyte memory, but the program had access to the CPU, and they could change the memory maps. Same also when they come to programs being only 16-bit, but the programs could do whatever they want. They could change the CPU over to 32-bit mode. And DOS did not have anything or no knowledge of processes. It was just a single process. It was your software. And lastly, there's no sound API in DOS, which means that all software written in DOS talk directly to the sound cards. So if you had a multimedia software back in DOS, it means that you had to implement hardware support for everything, and that your multimedia program or game would be an operating system in itself when you compare it to modern standards. So yes, I started to allocate my main function, mains, and I copied that into a blank project and see if it could compile. And first thing notice is lots of things can be removed. So for instance, to check if you had a virus infection in DOS, doesn't really matter. So that we could easily remove. So next dependency it got was to a list of initializers. And the first in this initializer was to configure all the interrupts. In Linux, we don't really need this, so lots of things we can simply remove. Next thing came on the list was actually support for DLL files in DOS, which is kind of special, since most people don't think DOS has DLLs, and it actually do not do that. But some C compilers had their own support for this. But hey, in Linux we have something similar. In libc, we can open SO files using some built-in functions in libc. So a lot of this functionality we could simply strip out and easily replace as well. So API conversions that had to be done. So DLLs we already mentioned, those we could remap to libc's own implementation. Next thing on the list is graphical output. And in Linux, it's more common if you have a text mod application to use N cursors. Or if you run it in a console, you can actually get direct access to the buffers using some special devices. Keyboard input is also quite simple. Actually, in Linux, we either use N cursors or you can read standard input. and you can map up all of the special keys and like up and down. Next thing on the list was the audio mixer routines. They were written in assembler. So those we will see in the next slide a bit. I had to rewrite them so they could compile with GCC. Audio hardware drivers. In Linux, we have the advantage that Linux can handle audio for us. And this we do either using Open Sound Systems or ALSA. Later, I also added support for X11 and SDL. So suddenly we have a big matrix of different inputs and output devices. And this also makes it possible to run it on quite large collection of different Unix-based OSs. But of course, things doesn't always work out. The first problem arrived when a person tried to run this on an old Mac, a really old one. It had an M68K CPU. And that has a different endian. And some of you probably never heard about an endian before, so do a quick introduction to that. So first, if we have our memory as a long list of addresses, each address can store 1 byte. So what do you do when you want to store 2 bytes into this system? Well, you can choose to have 1 byte before the other, and both are correct. This is called little endian and big endian. And different CPU architectures and file formats choose to implement different ones. And why they choose, I don't know. But it means that whenever you load a file, we need to be aware of which endian it is stored in and convert it to whatever your local CPU actually expects. So with that out of the way, I mentioned that original mixers were written in assembler. And this was probably chosen because C compilers and C++ compilers back in the days were not very efficient with the code they produced, and the machines were not super fast. So with code that really very important would be handwritten in assembler, and you would call up these functions from your program. I initially chose to keep the assembler mostly as is, hard to see on the slide, but I was put this inside a little wrapper, and you can glue it into C as is. But you need to inform GCC about which registers are used as inputs and outputs. And suddenly, GCC can use the assembler block as is. But this is not very compatible when you want to have different CPUs, and also when you want to have 64-bit support. So all of the assembler functions need to have alternative versions in C. And even had one contributor writing the assembler functions to C for the floating point unit. So I didn't have to do everything myself. So let's jump, one more thing. Background idler. Back in year 2000s, machines were still a bit slow. And if you open the file browser inside Cubic Player, the music would every now and then skip a bit. So I choose to look at how this was solved in DOS. And in DOS, they would use a timer interrupt. And in Linux, you don't have interrupts in a program. But for timer, we have something similar. We have something called sig timer, and you can instruct the kernel to give you a signal on that signal handler at a given interval. So I chose to copy-paste the original code from Cubic Player for this. But it kept on locking up my console. And early in the night, I initially did not know why this happened. So I was able to get out a little piece of code, and initially thought it would be a bug in my code or GCC, and that my code just simply locked up my terminal, but the machine was still okay. It turned out to not be that. It turned out that I had hit a 0-day exploit by pure accident. So it turns out that the FPU is actually async with the rest of the CPU core. So when you do a store and restore of all the registers in the FPU, it doesn't happen immediately. It takes a little time before it actually happens. And what I did in the original code that I kept from DOS is I wanted to preserve the state of the FPU, because I didn't know if this was necessary to do or not in a SIG timer. And I had, by mistake, left out a little star. So the pointer was not dereferenced enough amount of time. So this code actually crashed, but the crash didn't happen immediately. It happened after the code returned back into the kernel space. And the kernel space exception handler routine didn't expect this kind of things to happen. So it kept on trying to restore the FPU over and over and over again. So you basically had a DDoS attack as long as you had a login access. So let's jump back in time to see how music used to be done before. And this chip looks like a weird name. It had many different names. It was sold under many different brands. And if you look deep inside it, we can see that it has a little pattern. We have 3 different pulse generators, they named it. Today we'll probably just call this square wave generators, and a simple noise generator. For each channel, you could choose to use the pulse generator or the noise, or both. They added what they named a global envelope generator. Very advanced name. Basically, it's a shape you can choose, and you can choose how fast this shape goes, and this can be used as your source for the volume adjustment. And each of the 3 channels could then choose one of these. To either choose the global envelope generator or a statically set volume. So how does this actually sound? Let's start a little demo program. Ta-da! So this is what a little louder. So we don't have so many knobs we can twist and turn. But hey, we can make sound. So let's get that closed away before we kill any more ears here. So let's see, next slide. So this chip had then 3 square wave audio outputs and was used in a big selection of products, including the ZX Spectrum 128, CPC, Atari ST. And common for all of these machines are that they have a very small amount of memory. And there were no standardized way for how the music should be stored and played back. And also a very limited amount of processing power per frame, which is why many games also only had music at the intro and not during the game as well. And at 2 different occasions, I got asked if I could implement support for different kind of music from games. The first one was to use iLet, which is a library that emulates the CPU and the sound chip from the ZX Spectrums and some similar machines. And the other request was EM files, which is using SD sound library. This one, instead of emulating the CPU, it just has stored one long dump of what the registers were. So how did this music sound? So, we can have music. Yes, music is nice. But how did they actually make this music? If we look into a dump of the music from one of those games, it's actually machine code. It was handwritten, And either the music composer need to learn how to make machine codes, or the music composer needed to cooperate with a programmer, and they need to cooperate for how to store the music and how it should be played back. So next up, next iteration of sound chips happened with the Commodore 64. Here they chose to have, instead of only square waves, they added support for sawtooth and triangles as well. And instead of having one global volume generator, each channel has its own they call it ADSR, which is attack, decay, sustain, and release, which basically means that you can choose how one specific voice will, how fast it will turn on and how fast it will turn off again when you play a note. And many people also say that one big change for this was that they added filters, that you could actually low pass and high pass the audio. So let's do a quick demo for this chip as well. So suddenly we have way more knobs we can turn here. So okay. So how did music sound then with the chip? And it was luckily that the music we played just recently was available on the Commodore 64 as well. So this is why Commodore 64 is said to be a very important change for how music sounds, because it's still only 3 voices, but since you have much more control of what those 3 voices do, the music sounds better. So, Commodore 64 also had more memory per standard, which means that the audio routines for rendering the music could also be bigger, which means that more games would actually feature music as the game was playing and not just before the game in the introduction.
There were also 2 chips to clock it.
Yeah.
Timer chips. Well, good, really good.
Yes. So, next thing up. Yes. Also, the implementation of playing back this music is using libsidplay, which is another open source project. And as well, SID files and music is still done using machine code, so not much has changed there though. So what's changed then? In the PCs, we were starting to see something named OPL chips. And these chips would feature up to 9 channels. Each channels would have 2 operators that were working in the same frequency, but they could be offset to have different harmonics. These could either play audio at the same time, or they could be looped back together, so that one output of the first operator would be added to the frequency into the second operator. And they had a total of 9 channels. 3 of these channels could be replaced with drums. So how does this chip then sound like? Suddenly we got even more knobs we can twist and turn. So let's do different harmonics for the 2 operators. But one thing that changed a lot since Commodore 64 is that all of the sounds are based on sine waves. So let's do a super quick demo of what music sounds like with this chip. So this would be the typical music of the start of the DOS era. So what other chips did we have around in the world? Let's jump a bit, since we have a short time. So Commodore didn't give up, even though the PCs were coming to the market. They come up with Amiga. And on Amiga, we had a sound chip, and they removed the idea of having these synth generators. Instead, you would play back audio samples. And you could choose how fast these audio samples are played back, which gives you different notes, and you can adjust the volume. The Amiga features 2 channels for the left speakers and 2 for the right. So a typical music editor on the Amiga would look like this, where you have 4 major columns controlling each of the 4 channels on the sound chip. Each of these columns you can subdivide into a note, which gives you the initial pitch of a note. We give it an instrument, so typical Amiga modules initially only had typical support for 16 instruments, hence only 1 digit. You could have a volume, effect, and parameters to that effect. So what kind of effects could we expect to do with this sound chip? It's so basic in design, right? You can actually do quite a lot by adjusting the pitch alone. Adjusting the pitch alone, you can probably do most of the things you can do on an electric guitar. Dragging your hand up and down, or vibrating, and all kinds of effects. And same also with the volume. By the volume you can slide up and down, or you can do tremolo by vibrating it quickly on and off. Next generation of audio in games. First comes the question, what was music? Well, you could divide music into instruments and note sheets. And here a new standard come up with keyboards, General MIDI. They went through all of the instruments and made it into a long database with major groups like pianos, drums, organs, and music sheets. One more. A MIDI file has 16 channels. Each channel you can look up as an actor, which means that you can only play one kind of instrument at any given time, but you can tell it to change what kind of instrument it has. So MIDI is basically a 16-person band. And the note sheet you can convert into a list of events, when to turn on and off different notes and what instruments to play. And in order to support MIDI files, we use Timidity. It's a very old project that loads sound fonts and renders the events given in the MIDI file to an audio stream. So, other file formats. MP3 files we're used to doing by using AMP, which is an old engine to decode MP3 files. It is buggy, and instead of bug fixing it, it was easier to just use libmod, which basically all these distros has installed anyhow. Same with OGG files, FLAC files. All of those are standard available in a distro, so just use the libraries. And WAV files was already built in. It's very basic, easy to parse them. So, do I get requests for new formats? Yes. But luckily, many of them are already open source, and you can copy-paste in and out from them. So, last slide. Thank you all. And making your project open source is not a negative thing. It makes it possible for you to get feedback, bug fixes, and if you abandon the project, others can pick it up and convert it. So, thanks to the original authors of Cubic Players, contributors, and all different libraries that are open source that I either can use as is or copy-paste out of. And some example sources of music. Thank you. I think my time is up, so I don't think we have so much time for questions. Yeah. So if you have any questions, you can either send them to FOSDEM or you can grab me out in the hall.